Okay, let's take a look at the last section, which is on the Bayes theorem. So the Bayes theorem is an application of conditional probability. It's a very special type of conditional probability. Definitely review the concept of conditional probability, how to better understand the condition, the Bayes theorem. So in the Bayes theorem, we have two types of probability. First one is a prior probability. Basically, it comes from the initial condition. Initial probability value originally obtained by before any additional information is obtained. Initial state or initial condition. Probability coming from the initial condition. We also have a posterior probability, which is probability value that has been revised after obtaining new information or additional information. So it's like a revised probability after the additional information is provided. So the probability of event A, given that event B have subsequently occurred, is probability of A versus conditional probability of event A, given that event B occurs. That's the definition of conditional probability, and then probability of B over A is conditional probability that conditional probability of event B given that event A occurs. And these two are totally different. And we also have a probability of B given that A not occurring. So this is the conditional probability of event B. Given that event A did not occur. So A bar here indicates A did not occur. Okay. So the formula is probability of conditional probability of event A given that event B occurs equal to probability of event A times probability of event conditional probability of event B given that A occurs over probability of event A times probability of conditional probability of event B given that A not occurs plus probability of A not occurring multiplied by probability of conditional probability of event B given that A not occur. So that's basically how we interpret this. I know the formula looks slightly complicated, but I'm going to show you some intuitive understanding of this formula and then use it in real life scenarios. So Bayes theorem generalized, the preceding formula used exactly two categories for event A, but the formula could be extended to include more than two categories, right? Could be 3 or 4 categories, and then we always must make sure those multiple events satisfy two important conditions. First one is these events must be disjoint, meaning there's no overlapping. They are disjoint events. Also, the events must be exhaustive, meaning that all these events combined includes all possibilities. So if you sum up the total probability equal to 1, this is what this second condition is about. So all those events include all possible outcomes. So total probability equal to 1. Now think about this. Let's say Dr. Foster remembers to take his umbrella with him 80% of the day. So here we know that Dr. Foster remember his umbrella or forget his umbrella. So there are two categories here. Remember, second category, forget. And if it remembers 80% and forget will be 20% because they're complement event of each other. He runs on 30% of the day when he remembers take his umbrella. He runs on 60% of the day when he forgets about his umbrella. And for the first part of the sentence indicates when he remembers taking his umbrella, it rains 30% of the time, meaning it did not rain on 70% of the days. And when he forgets to take his umbrella, it rains on 60% of the days. That means 40% of the day it did not rain. So we can create a tree diagram. So this tree diagram is very useful in terms of understanding this. So we first of all we break down remember. If he remembers to bring his umbrella or forget to bring his umbrella, so 80% of the time he remembers, 20% of the time he forgets. And when he remembers take his umbrella, 30% of the time it rains, right? And not rain. So 30% of days rains, 70% of days it did not rain. Again, these two are complement events. And when he forgets to take his umbrella, it rains on 60% of the time. So on the other 40% of the time it did not rain. Now the given conditional probability here is what is probability that he remembers his umbrella when he rains. So he remembers given that when, meaning it's a given condition in range, given that he remembers. So this is how we set up the conditional probability. So if you're gonna look into when he remembers he range, right? Forgets also range. So we're looking at percentage of the time when he remembers umbrella when he rains. So percentage of that will be 80% times 30% divided by 80% times 30% plus the other condition when he forgets also rained. So you want to find out the percentage under the given condition that he rains and he remembers and he forget. Okay. So 20% times 60%. So 30% is 0.8 times 0.3 over 0.8 times 0.3, adding 0.2 times 0.6. So this is 0.24 over 0.24 plus 0.12 is 0.36. Simplify it to third. But if you want to turn it percentage, it will be 66.7%. But yeah, so the basically you can also apply the formula, means same thing, right? You will get the same result. But we just try to understand this intuitively based on the given information here. Okay. So this is basically how we apply Bayes' theorem, solve the real world problems. Now, another example could be in a factory, machine X produces 60% of the daily output. Machine Y produces 40% of the daily output. Okay, so we have two machines, X and Y. 2% of machine X's output is defective. 1.5% of machine Y's output are defective. One day an item was infected at random and found to be defective. So this is the given condition. Given condition is the item they found is defective item. So we want to find out, we want to trace back, see which probability value was produced by machine X. Remember, both machine X and machine Y produce defective items with a certain probability. Now we just want to trace back to the machine X, and that's how we separate it. So this given condition, separate the applications of each machine. Okay. Okay, so let's show you the details. Copy this. Okay. First one, let's draw the tree diagram. Very for tool to have. So we do have two machines, right? X or Y. And then machine X produces 60% of outputs, and machine Y produces 40% of outputs. Remember, machine X produces good outputs and then also the bad outputs, good and bad, defective, good and defective. So 2% of the outputs produced by machine X is defective. That means 98% of them are good items. Now for machine Y, only 1.5% of them are defective. The remaining of them must be good items. So 1.5%, and this is 98.5%. So we have all this information provided. Now the question is asking us what is probability that it's produced by machine X given that it's defective items. Defective item comes from two sources. First source is X produce defective or Y produce defective, but we only want to make sure it's percentage of machine X producing defective items. If you look at conditional probability, that would be X given that it's defective. Okay, and the bottom will be using the probability of X times probability of X given that defective. And then the second one will be not X. Probability not X meaning probability of Y. Machine Y produce, so machine Y produces defective item. Okay, so we look at this probability of X. Machine X produces 60% of outputs, and out of the 60% outputs, 2% are defective, so most are about 2%. On the bottom, so the first part is the same, 60% and 2%. The other part, probability of Y, which is 40%. Probability of machine Y produce defective items, 1.5%. So now this is 0.6 times 0.02 over 0.6 times 0.02 plus 0.4 times 0.015. This is 0.012. Top is 0.012 plus 0.4 times 0.015 is 0.006. Now if you simplify, it will be 0.012 over 0.018. Reduce it to the, again, it's 2/3 chance. If you look at it, it's 66.7% in between the percentage. So this is the conditional probability you're looking at. Right? So Again, in order to solve any conditional probability problem, application problem, like in this case using the Bayes theorem, we draw a tree diagram and then summarize what a given condition are, and then you can solve it step by step. And that's pretty much what we have here on PowerPoint.